Welcome to part 4 of my video playlist about carbon dioxide. This video is about the preparation of carbamates, organic carbonates and ureas by reaction of amines and alcohols with CO2. These reactions have been studied a lot in recent years because solutions of inexpensive amines can be used to reversibly capture carbon dioxide from the exhaust of coal or gas-fired power plants. For organic synthesis, direct carboxylation of amines or alcohols with carbon dioxide is only rarely used because there are more reactive and more convenient reagents available. Anyway, with the specific examples below, you should get a feel for the scope and limitations of this chemistry. Primary or secondary amines react reversibly with carbon dioxide to carbamic acids. Because of the high stability of CO2, as discussed in part 2 of this playlist, carbamic acids and their salts readily decarboxylate at room temperature. It is however possible to esterify carbamic acids by electrophilic alkylation at oxygen with hard electrophiles. Carbamic acid esters are more stable than carbamic acids and do not usually decarboxylate. Carbamic acids can also be esterified by dehydration followed by reaction with an alcohol. If a primary amine was used, this dehydration would yield an isocyanate. Iminium salts, as the ones sketched here, or isocyanates are highly reactive and readily react with alcohols or amines to the corresponding carbonic acid derivatives. One potential problem of the reaction of amines with CO2 is the formation of ammonium bicarbonates. If water is present, carbon dioxide will be hydrated to a certain extent, and carbonic acid will then protonate the amine. Ammonium salts are no longer nucleophilic and will not yield any carbamic acid when treated with CO2 at moderate temperatures. Faster and cleaner conversions of amines to carbamates are usually achieved by treating an amine first with some reactive carbonylating reagent, for instance phosgene, carbonyl diimidazole, or a diaryl carbonate, and then with an alcohol. In the case of primary amines, these reactions can proceed via an isocyanate, which is much more reactive than carbamoyl chlorides or carbamic acid imidazolides. Alternatively, the reaction of amines with chloroformates yields carbamates directly, in one step. Chloroformates are unstable, however, and tend to fragment into carbon dioxide and alkyl chlorides with time. Potential byproducts are ureas and carboxylated ureas, and the order in which reagents are mixed can be critical. With phosgene, for instance, the amine must be added to an excess of phosgene to prevent the formation of ureas. As a byproduct, first an ammonium chloride is formed, which will however also react with phosgene upon heating. Further routes to carbamates include heating amines with alcohols and urea or with organic carbonates. Oxidative carbonylations with carbon monoxide have also been reported, as have dehydrogenations of formamides to isocyanates. Let's check some specific examples. Here butylamine reacted with carbon dioxide under anhydrous conditions, and the resulting carbamic acid was then alkylated with benzyl chloride and various bases. The yield of carbamate increased with the steric crowding of the base, that is, the slower the alkylation of the base, the higher the yield of carbamate. Even simple unactivated alkyl chlorides can alkylate carbamic acids. The quaternary ammonium hydroxide catalyst probably reacted quickly with carbon dioxide to an ammonium carbonate, which was less nucleophilic than the carbamic acid salt and did not consume any alkyl chloride. Alkyl bromides are more reactive than chlorides, and here the alkylation of an intermediate carbamate was complete after 6 hours at room temperature. Still more reactive are alpha-haloketones, for instance brominated acetophenone, also called phenacyl bromide. Here the alkylation only required 5 minutes at room temperature. No alkylation of the hydroxy group or racemization occurred. Instead of gaseous CO2, quaternary ammonium bicarbonates can also convert primary or secondary amines into carbamic acids. In this example, the intermediate was alkylated in excellent yield with ethyl tosylate. Epoxides are also suitable alkylating reagents for carbamic acids. This example shows that anionic carbamic acid salts can react faster than neutral amines with epoxides. Dimethyl carbonate can act either as electrophilic carboxylating reagent or as electrophilic methylating reagent. Treatment of phenethylamine with an excess of dimethyl carbonate and carbon dioxide gave mostly a methyl carbamate and about 15% of methylated products. Carbamic acids can also be esterified not by alkylation with electrophiles, but by acid-catalyzed replacement of the hydroxy group by an alcohol. This would be similar to a normal acid-catalyzed esterification of a carboxylic acid. In this example, the carbamic acid formed from morpholine and carbon dioxide was esterified with triethyl orthoformate. Morpholine also reacted with the methyl formate formed as byproduct to yield a formamide. In this example, the diethyl acetal of acetone was used as dehydrating and esterifying reagent. The reaction was run at 200 degrees Celsius, however, and electrophilic ethylation of the carbamate cannot be completely ruled out. Another possibility is esterification with an excess of tetramethyl orthosilicate. Again, a high yield of carbamate resulted. Instead of thermal or acid-catalyzed dehydration, carbamic acids can also be activated by Swern-type reagents. These are formed when DMSO is treated with a reactive acyl chloride or anhydride at low temperature. When triethylamine and a carbamic acid are added to this activated DMSO, dehydration occurs. In this example, an isocyanate was prepared this way, which then reacted with benzyl alcohol to the benzyl carbamate. In this interesting example, a urea was prepared from anthonyl amide and carbon dioxide. As dehydrating reagent, one equivalent of triphenyl phosphide and DBN were added. The mild conditions suggest that a Mitsunobu-type reagent was formed from the phosphide. This requires, however, an oxidant, and the only candidate for that job would be carbon dioxide. So, formic or oxalic acid or some other reduction product of CO2 must also be formed during this reaction. Examples have been reported of the vinylation of carbamic acids with alkynes. Here, such a vinylation was catalyzed by 2% of ruthenium chloride and a mixture of two stereoisomers resulted. If propagylamines react with carbon dioxide, the resulting carbamic acid can undergo intramolecular vinylation at oxygen, as in the first equation on the slide. Here, a small amount of palladium acetate was added as catalyst, but alkynes are sufficiently electrophilic and this catalyst was not strictly necessary. With the parent, sterically undemanding propagylamine, the reaction mostly yielded a cyclic urea by reaction of the amine with the initially formed oxazolidinone. Instead of preparing a carbamic acid from an amine and carbon dioxide, an alcohol can first be converted into a carbonic acid monoester and after activation reacted with an amine. Alcohols do not, however, react with CO2 as readily as amines do. Activation can then yield a mixture of activated carbonic ester and activated alcohol, and the yield of final carbamate might be low, as in this example. Here, the carbonic ester was activated with methane sulfonic anhydride. Many byproducts were probably formed, and this is definitely not a good way to prepare the target carbamate. Aziridines are similarly reactive as epoxides and can yield oxazolidinones when treated with carbon dioxide and a suitable catalyst. Here, a small amount of an iron complex was used for this purpose. Only one of the two possible regioisomers was formed. I'll show you now some examples of the preparation of organic carbonates from carbon dioxide. Here, a homoallylic alcohol was treated with tertsbutyl hypochlorite and sodium bromide under CO2. Bromination of the CC double bond gave an electrophilic intermediate, probably a bromonium cation, which activated carbon dioxide and thus facilitated the addition of the hydroxy group to CO2. The final product was obtained in good yield and with high diastereoselectivity. Many examples are known of the insertion of carbon dioxide into epoxides to yield cyclic carbonates. Even epichlorohydrin, the starting material of this example, reacted cleanly with CO2 to the expected carbonate, without any displacement of chloride. An almost non-basic mixture of sodium iodide, triphenylphosphine and phenol catalyzed this transformation. Here a rather unusual catalyst was used, a slightly basic phenol-derived betaine. Again, the yield of carbonate was excellent. Even weak acids can catalyze this transformation. In this example, 10% of DBU hydroiodide was used. One final example with 2-aminopyridine as catalyst. All these catalysts probably work by cleaving a small amount of epoxide and thereby generating a strongly basic and nucleophilic alkoxide, which then acts as the true catalyst. Like the propargyl amines discussed earlier, also propargylic alcohols can be converted into cyclic vinyl carbonates by intramolecular vinylation of an intermediate carbonic acid. This example here is a one-pot sequence of Sonogashira arylation of the alkyne, followed by cyclization and a final Heck reaction. Also, ureas can be prepared directly from amines and carbon dioxide. Actually, urea itself is prepared as a fertilizer on a huge scale from ammonia and CO2 by heating ammonium carbamate to about 190 degrees Celsius under pressure. For structurally more complex ureas, however, milder conditions are required. Here, phenethylamine reacted with CO2 already at 120 degrees Celsius and ambient pressure. An oxovanadium alkoxide and a tertiary amine were the catalysts, and no stoichiometric dehydrating reagent was required. In this example, the intermediate carbamic acid was activated by carbon tetrachloride, which sometimes reacts as a synthetic equivalent of phosgene. Here, a silane was used as a stoichiometric activating reagent of the intermediate carbamic acid. In the presence of transition metal catalysts, silanes can react with alcohols or acids to silyl ethers or esters and hydrogen. Alternatively, carbon dioxide may have acted as an oxidant. Instead of CO2, carbon monoxide can also convert amines into ureas, but an additional oxidant is required. Here, the oxidant was oxygen, and the reaction was catalyzed by 0.1% of palladium iodide. Unfortunately, under these conditions, an oxalamide was the main product, not the expected urea. By further lowering the amount of catalyst and by diluting the carbon monoxide with carbon dioxide, the target urea was obtained in high yield and the risk of explosion was also reduced. In this example, iodine was the oxidant and tungsten carbonyl the catalyst. No oxalamide, but mostly the expected urea was obtained, along with a small amount of a cyclic carbamate. On this and the next slide there are some further examples, which you can also find in the description of this video. As usual, there's a PDF version of the slides under the community tab of my channel. The next video of this playlist is about the decarboxylation of carboxylic acids, including oxidative decarboxylations leading to the formation of carbon-oxygen, carbon-halogen or carbon-carbon bonds. So long.